My name's Alan Stokes. I'm an engineer at Google. I work on the Android security and privacy team. I've been working with SELinux for about the last 6 years. It's not really my full-time job, but I do a fair amount of it. I write policy. I do a lot of reviews of policy. I'm in the owner's file, but I kind of feel that I'm still an apprentice. I'm still learning things about SELinux. It's a complicated subject. I probably did slightly too many slides here, so I might go through this a little bit quickly. I suspect some of the basics may be familiar anyway, but do feel free to stop at any point.
We don't have a particularly packed schedule, so it would be okay for you to go over by 10 minutes, maybe.
Okay, well, we'll see how we get on. Anyway, let's start with the obvious thing. What is SELinux? SELinux is mandatory access control for Linux. So normal file permissions are discretionary access control, which means they control access perfectly well. You can set them any way you want. You have complete discretion. You can set them in very, very bad ways if you want. It's up to you. SELinux is very different. It is mandatory, and it's not you setting it. It's the administrative policy. It's so the notionally it's sort of the owner of the system, or in the case of Android, the manufacturer of the system who decides what the policy is. It's defined as part of the device. Apps can't change it. User can't change it. It's just there. It was originally developed and proposed by the NSA, which freaked a few people out. But the reason why they're interested in mandatory access control is because this is how governments work. If you're given a top secret document, you can't decide to give it to someone else who hasn't got clearance. You absolutely must not do that. And there are laws and processes and systems in place to make sure you can't do it. These days, it's a standard Linux subsystem. It sits on top of the Linux security module framework, and it's just there. And I suspect Android is one of the bigger install bases of SELinux, but it is used in other systems as well. But you get both. So the discretionary access control is still there. Any access you do has to pass both sets of rules. If either says no, you don't get in. And neither of them allows you to bypass the other. Well, mostly anyway. Mandatory means mandatory. So the policy is set. You can't change it. You can't load a different policy. You can't disable the policy. And actually, the reason you can't do that is because the policy says so. It's perfectly possible to create an SELinux policy that allows you to do these things, but Android doesn't. This is not strictly true on a user debug device or using a non-user build. ADB root runs a shell in a domain. Well, I'm probably getting ahead of myself here. In a permissive mode, which means that basically none of the rules apply to your shell, which means you can do things that would violate the policy, including turning SELinux off for the entire device. That can be quite useful when you're prototyping something or debugging. It's a terrible idea from a security perspective, but it can be useful. So how does it work? It's labels all the way down. So everything in SELinux has a label, sometimes known as a context. SELinux has a lot of terminology and quite often multiple words for the same thing, just to keep everyone on their toes. So processes, which we call domains, files, sockets, apps, properties, services, loads of other things, all have a label, and we refer to them all as objects. The labels are normally assigned completely automatically. It's not something you have to worry about generally. It is possible to override the labels if you have the right permissions, and there are ways in which labels can change automatically or manually. The default labels for things are mostly specified in a whole bunch of configuration files. So genfs context, for example, defines the labels for the file systems that are hosted by the kernel itself, like /proc. File context says what files on the storage should have as labels. And then there's property contexts for properties. There's SE app contexts, which is about apps. That is actually one of the more complicated ones. There's some documentation at the top of that file which explains how it works, which actually I'm quite proud of because I did a lot of work tidying that up. But in general, just to summarize enormously, it tends to allocate the label untrusted app to any third-party app that doesn't have any special meaning to the system. Most of these labels, let's say, come from the configuration file. File labels are special in that they are actually stored as part of the file system. So each file directory has an exatra which contains its SELinux label. There are mechanisms to make sure you can't actually access that exatra, but it is there. So it's possible for a file directory actually to have its label set to something that's not what the file context says it should be. There's a command restore con which will fix that. That's run automatically by init on a whole bunch of files when you boot. But it's complicated, and occasionally you can end up with things that don't have the permission that have the label you might think they should. If you do want to try and figure out what labels things have got, PS minus capital Z will list the SELinux label for each process that you see. LS minus capital Z will tell you the label for each file you can see. And if SELinux decides you can't do something, it logs a denial message, and the denial message tells you the labels. So there is some visibility there. I should perhaps explain what a label is. So a label is just a string. They're stored in the kernel as strings. It's kernel separated. There are 4 fields, one of which contains 2 fields. So it's user, role, type, level, and level itself is severity and categories. You can completely and utterly ignore the user, the role, and the severity because they have no use information on Android and don't affect anything. And most of the time, all we care about is the type. That's what most of the policy talks about. SELinux has various different sort of subsystems, but the most important one is called type enforcement, otherwise TE, which is why all the policy files tend to end in the .te extension. Categories are also important. I'm going to talk about them a little bit later because they're kind of unrelated. Here's a couple of example labels. So the first one was a label on a file, and it's a system data file, which is one of the defined labels in the policy. The second one came off a process which was actually running a system-signed app, and that has some categories attached to it for reasons which, again, I'll talk about in a little while. It all comes down to rules. The policy is essentially a very large collection of rules. The starting point is that everything is forbidden. If you don't have a rule allowing something, then you're not allowed to do it. So you start from nothing, and you have to explicitly allow all the things you want to be able to do. And the policy is just full of rules allowing specific accesses. So this is a slightly randomly chosen rule from the system policy. It is saying that a process that's labeled APEXD, which is actually the APEXD process, is allowed to access files labeled with the Apex metadata file label. And it's allowed to create file permissions is actually a macro, which expands to a whole list of permissions, but it's basically allowed to read, open, write, create files, which is quite a broad set of things. So the syntax is you say allow a source type to access a thing with the target type label of a target class with specified permissions. The reason the class is there is that different classes of objects like files, sockets, processes have a different set of permissions. The permissions are called access vectors for no obvious reason. And the other thing I should say is that here I've got one source label, one target label, and I've got a whole set of permissions, but there's actually a syntax where you can put things inside braces and specify multiple. And there's other bits of notation. The notation is actually relatively easy to figure out when you look at it. So that's allow rules, and basically the policy has a lot of those. There are a few other things that you tend to see. So there's a don't audit rule, which it's the same syntax. It's just that instead of saying allow, you say don't audit. And what that says is just, okay, this is still, if this isn't allowed, then you deny access. The caller gets an e-access, e-perm, whatever. But it doesn't get put in the log. So what we're saying essentially is, we know this denial happens. It's harmless, and we basically don't care. And we don't want it in the logs, messing up the logs. It's not always a good idea to do this, because if someone puts some new code in that triggers the same denial, it won't appear. Sorry? And ideally, you don't want processes wasting cycles doing things they're not allowed to do. It would be much better if you could fix the code to not do the thing it's not allowed to do. But for all sorts of reasons, that's not always possible. So you do see these in various places. A much more exciting rule is never allow. This is kind of curious because I said nothing is allowed unless you put an allow rule in. So never allow doesn't actually have any runtime effect whatsoever. It's a compile time thing. It's saying there must not be any rule in this policy that allows this thing. That means anyone who does attempt a policy change that does one of these things, when they try to compile the policy, they'll just get a compilation error, which is kind of a hint that this is a bad idea. And we'll talk a bit later about system policy and vendor policy. The never allow rules apply to vendor policy. So system policy, when it ships, doesn't violate the never allow rules, but the vendor policy is also expected to comply with them. And the never allow rule is essentially saying, don't do this. This would be a really bad idea. We do sometimes relax never allow rules to allow things that weren't previously allowed, but by and large, it's a big sign saying this is bad. So if you do something and SELinux decides you can't, and if you don't audit it, then you get an AVC denial, which is written to the audit log and to the event log. AVC stands for the access vector cache. That's of no relevance whatsoever, but I just thought I'd mention it. So this is an example denial that you might see in the log files. It's actually quite information dense. I've tried to highlight the bits that kind of matter. So denied is kind of important. That's saying you tried to do something and we didn't let you. You also get told what you were trying to do, what the source label was, target label, target class, and sometimes some extra information. So what this denial is saying is that some process running with the shell type, which is probably someone running something in the shell, tried to connect to a Unix stream socket. That's a Unix domain socket, which has the type netd. And it actually tells us what the command line was and what the path of the socket was. You don't always get that sort of helpful context information. Sometimes you only get an inode number. Sometimes you get really very little at all. But what's generally useful is just to look at what the surrounding log lines say. So ideally, whatever just got an error code returned will log that it got an error, and then you can figure out what's going on. Because we all log our errors, obviously. If you are hitting denials or you're trying to figure out why something isn't working, my top tip is in the shell, if you run audit control -R0, that turns off rate limiting. Otherwise, you only get a maximum of 5 audit logs per second. And sometimes you generate a lot more than them. And actually seeing all of them can give you a good picture of what's going on. One thing I should mention, netd, this Unix stream socket here is labeled with the netd label. Netd label is actually the label we apply to the netd process, which handles a whole bunch of networking stuff. And so you'd expect that label to be on a process rather than on a socket. But for things like sockets and for various other things that are closely associated with a process, when the process creates them, they inherit the process's label. This is one reason why the class matters. So the netd process has the netd label, but the sockets that netd has created also have this label, and the policy has to take account of that. So I keep talking about the policy. The system policy, which in theory is supposed to be the same for all Android devices. I mean, it's developed in AOSP, and it's intended to be common to everyone. Lives in the system's SE policy directory. It is mostly .te files. There are a lot of them, which have all the rules in them. There are a whole bunch of other config files. When I first came across SELinux, I felt that someone was deliberately hiding them, because it took me a long time to notice that not all the files ended in .te. But they are in there, and they can be quite interesting. As I said, there are macros. When we compile the SE policy, we run it through the M4 macro processor, which is, well, I always found M4 slightly terrifying. We don't do anything too exciting with it. But there's a bunch of useful macros that are used in the policy. There's a couple of files that contain these. The global macros is the one that defines the various common sets of permissions, like create file perms, which is just a macro that expands to a set of common permissions that are often assigned at the same time. The TE macros are macros that are useful in TE files. They're used to avoid duplication. So the idea is, if there's a set of rules that we quite often go together, then we can define a macro for it, and you just invoke the macro name, open parentheses, parameters, and that just does something to the policy by generating some rules. So as well as the system policy, any real device will also tend to have device or vendor specific policy, which is not generally as part of the AOSP tree. Although actually the vendor policy for released Pixel devices is public and is part of AOSP. So if you want to have a look at it, it's out there as an example. And the point of the device policy is, well, some of it is just, the system policy will say things like the graphics subsystem is allowed to talk to the display, but the precise path to what the display driver is will vary by device. So you need something that says this driver over here should be labeled as this is the video driver. Sometimes you need to define policy for device specific processors or drivers that simply don't exist in the AOSP source. So there needs to be device specific policy for that. And in either case, the vendor policy, the device policy, can reference the public system policy. System policy won't directly reference the device policy because it can't, because it's common to all devices. But you're allowed to refer back. And we'll talk a little bit more about the vendor and public split a little bit later on. One thing I find myself doing quite often is trying to figure out what it all means. What in fact are the rules affecting some particular process, or why am I being denied? If you look through the files, the files are organized by what is being allowed. So the first thing that comes after the allow. So if you've got a rule that says allow foo something, that should be in foo.te, and that's mostly true. And code search over SE policy I must do half a dozen times a day, I would think, and that is really helpful. It is slightly complicated by the existence of attributes. I haven't really mentioned those so far. You can create an attribute in the policy, which is a way of representing multiple labels that have something in common. Attributes can be applied to multiple types. Types can have multiple attributes. And a rule can, instead of specifying a type, you can specify an attribute. Core domain is so the statement below there says the APEX-D domain has the attribute core domain. And then a rule could say, well, core domain is allowed to do this, or core domain is not allowed to do this. There's quite a lot of them. There's fairly broad attributes like domain, which is every process, or file type, which is any type that's used to label a file. There's a label called app domain, which is any process that is an Android app in any form. And they use quite extensively in the policy, but it does mean that if you're trying to figure out what can this particular process do, you need to figure out what attributes apply and search for those as well. That can get very confusing in complicated cases. So what I sometimes do is just pull the compiled binary policy from the device. You can do this using ADB. I don't think this requires root. You have to use this exact syntax because the policy file is actually quite locked down. But once you've done that, you have a binary policy on your development machine, and there's a command line tool you can get from the usual places called SE search, which you point at the policy file and you say, tell me. You can search basically by the source type, the target type, the class, the permissions. So you can sort of say, who can access this file, and it'll give you just a list. That could be interesting itself, and you can then go back to the policy and try and figure out where the rules that actually apply on the device came from. Okay, I've kind of run out of stuff to say about how it all works. So the next question is, well, how's it used? What is it for? The title of the talk was how do we use it to make Android secure, and that's kind of the point of this. I think it's fair to say that the existence of SELinux, or the use of SELinux in Android is kind of the bedrock of Android security. I mean, I can't remember now which version it came in, and it's quite a long time ago. But it has made a huge improvement in the security and our ability to be confident in the security of things. One way we use it is implementing least privilege. So it's a good principle of security. Every process should only be given the access it actually needs. The counterexample would be running things as root without SELinux means you can pretty much do anything you want. That means that if your process is compromised, game over. If we give a process only the access it needs, then if someone manages to compromise that process, I mean, that's bad, but they can only get the process to do what it's allowed to do. So if it's not allowed to do anything particularly terrible, the attacker doesn't really achieve very much. One way of, you have to pick a sort of granularity. I mean, but one thing we have done in the past is to take complicated subsystems. The media subsystem is kind of a standard.
Somebody seems to have their microphone not muted.
I see there's a question in the chat. I'll get to that in just a second. What I was going to say, so the media subsystem, you don't want to have domains that are high risk also having high privilege. So again, a few years back, the media subsystem was split up into separate processes. So the ones that are high risk, for example, running codecs on untrusted media input. And codecs have a fairly terrible reputation for security vulnerabilities. The media input can be controlled by the attacker. So there have been a whole bunch of times where people have managed to attack those processes. If you make that a separate process from the ones that have high privilege, like the ones that can access the drivers for audio, video, and so on, then the attacker who managed to successfully break the codec can't access the driver, so they can't then attempt to do further attacks and escalate their privilege. They can do what they can do inside the codec process. That's largely fairly dull, and that makes the whole system more secure. And we also use SELinux as part of the sandbox for untrusted apps. The apps that you download from somewhere are inherently not trusted. We don't want them to be able to do everything. We do want them to be able to do a lot of things, but we can make sure that the policy allows them to do the things that make sense and does not allow them to do extra things. One of those things is we restrict access to device drivers. If you can talk directly to a device driver, if the driver is buggy, you might be able to compromise something. So we try to make sure that most processes, the only processes that can be accessed to device driver are ones that really need to. And that particularly applies to ioctls. So we don't just even if you have access to device driver, we don't let you use just arbitrary ioctls. They generally have to be specifically permitted. There's actually a very weird SELinux syntax, allow expert, that implements that. And the nice thing about all this is that quite often, if there's a vulnerability in a driver or somewhere in Linux, if no untrusted code, or if no code at all is able to access the vulnerable area because SELinux policy stops it, then although it'd be nice to fix the problem, Android is not vulnerable because no one can actually get at the problem. I should get back to that question I mentioned. So you should. So if you're getting things denied, but you're not seeing the denials, which I think is what you're saying.
Can I just interject here? So this is a message from Ahmed.
Yes, I'm here. Can you hear me?
Yes,
Yep.
yes, I can hear you. Yeah.
Yeah.
Go ahead, Ahmed.
So the thing is, you have an application that's running on Android, and then it doesn't work as it should, and you don't see any denials in the logs. But as soon as you disable SELinux, and then you try to test the app, it works, but you don't see any permissive denials as well, which you should normally see. And but if it works when it's permissive, then that definitely proves that SELinux is causing some issue.
That certainly indicates it. I have seen that. The various things I would check is firstly, I mentioned the turning off the rate limiting. It may be that the log messages you care about are being thrown away by the log limiting, and you're seeing ones that aren't terribly interesting to you. So I always do that as a first step. The other possibility is that actually it's not SELinux at all. I mean, I know if you say if you turn off SELinux, that is kind of a good example, but sometimes you get things being denied. You think that must be SELinux, and actually it turns out that it's a normal Linux permissions problem. I've done that several times. And the other possibility is that someone somewhere has put a don't audit in for whatever it is you're trying to do. And so, it would be lovely if there was a way of building the policy saying ignore all the don't audits. I don't know of a way of doing that. But yeah, in which case, all you can really do is if it, then you're kind of guessing a bit. And the only other thing I would say is, like I said, I mean, ideally, anyone who gets an error code back when not expecting it would log what the error code was, what they were trying to do, and then you can just say, "Oh, well, it's obviously that." In real life, of course, this doesn't always pan out, but
I think it's either of that cases. Like either it's not audited, and there is no way. You're right. I tried to look if there isn't a way to like override that you can audit all of the don't audits just for debugging. So it's not possible for some reason.
Yeah, you'd have to. I mean, you could, of course, just delete them all. I'm sure there's a trivial sed script or something that would do that for you. But
But then it's too much for you to filter out. You never know which one is causing that problem.
Well, we don't have too many don't audits, and they tend to be for things that that we're pretty sure shouldn't be happening. But that is a possibility.
Okay. I think I'll try the rate limiting thing. Probably that works out. I think
that has definitely helped me on a lot of occasions.
Okay. Thanks, Alan.
No problem. Okay. Yes. Let me move on a bit. So another really important use of SE policy is user and app isolation. I don't know how familiar you are with multiple users on Android. So Android has the idea of a device that's shared by multiple people, multiple actual human beings, like a family tablet multiple people use. And they're called users. This is possibly the worst use of terminology anyone ever came up with, because users is a terribly overloaded term. But anyway, they're called users. And the rules are basically that if you have two people who are sharing a device and they each have their own user account on it, then one user shouldn't be able to access the other user's data. I mean, that's just a privacy thing. Also, if both people happen to have the same app installed, the app shouldn't know that there's another user on the device, and shouldn't be, the app while running as me shouldn't be able to see what the same app is doing for my friend who also has an account. And even if you only have a single user system, which is like most phones, I suspect, there's also isolation between apps. So if you have two different apps on the device, they should never be able to see each other's data. It used to be the case that we allowed apps to mark their private data files as world readable or even world writable. That comes into the category of things you're allowed to do, but you really shouldn't do. But these days, that's no longer true. So even if an app does manage to make its directory world readable at the file system permissions, SELinux will stop other apps from being able to access it. Actually, this is one of the most important parts of the Android security model. The app private data files are extremely well protected. So the user doesn't have direct access to them. They can only access them through the app. The system, by and large, doesn't have access to them. There are a few very trusted processes that need to have access, but in general, not much does. And one app can't access another app's data files. But the mechanism for that has to be something other than type enforcement, because all apps get the same type by and large. Well, that's not strictly true, but all untrusted apps get the untrusted app label, and all app data files have the app data file label. So how can we say app 1 can access app 1's data, but app 1 can't access app 2's data. And this is a whole separate subsystem in SELinux, which is where categories come in, which I mentioned a while back. Multi-level security. I should explain that almost nobody understands this, and most of the time you can ignore it, except when you can't. It's a completely separate from the TE rules. It's all encapsulated in one file called MLS. It has its own syntax. It's completely different from the rule syntax. I'm not going to show you the rules because frankly it's very complicated. Like I say, not many people understand it. But what it basically says is when the MLS rules apply, which they do for example, app data files, the source label must include at least all of the categories that the target label does. And then what we do is we encode the user ID and sometimes the app ID into the categories. So I think earlier we saw the categories C512 and C768, which I happen to know encode the fact that this belongs to user 0. If it was user something else, it would have a different pair of categories. And this is where the magic comes. So if a process from one user tries to access a file from a different user, or a process that belongs to one app tries to access a file for a different app, the categories don't match. And so the MLS rules say no. And just like you have to pass both the discretionary and the mandatory access permission, you have to pass the type enforcement rules and you have to pass the MLS rules. There are a couple of special types, MLS trusted object, MLS trusted object, that let you bypass this, but they're fairly specialist. That's the things that we know are safe to cross users. The main time this come up is I sometimes see people saying, I have a denial saying that A can't access B, but I have a rule saying allow A to access B. And the first thing I do is check what the categories look like, and I'll say, that's you're trying to do something in the wrong user. And then my final example of what we can do with SELinux is all about the system and vendor. Again, quite a long time ago now, there was a thing called Project Treble. This was all about making it easier to update Android versions on existing devices. Because when a device, when someone puts a device together, like I said, you need vendor policy for it. You need drivers for the specific hardware that's part of the SOC, a whole bunch of specific policy. Actually, can I just? I'll stop there. Chris, you just put something on the chat.
Yeah, sorry, I was going back to the thing that Ahmed was talking about, and it kind of rang a bell with me, so I just did a quick check. So there are other things when you set SELinux into permissive mode, not only does that suppress checking of or the failing of SELinux calls, it also silently disables SEComp. So SEComp is a completely separate thing which filters which system calls an application can make. So it could be nothing to do with SELinux at all. It could be something else that is masking the problem that you may see.
I was thinking of mentioning SEComp, but I decided not to. But are you sure that turning off SELinux turns off SEComp? Because I didn't think that was true, but I've never really investigated.
It's in my notes, so it must be true. I believe so. I've written it down here, so it was true when I wrote it down. Let's put it that way.
Interesting. Well, like I say, I'm still learning stuff about this. So
yeah, this is also new for me. So is there a way to see if this is caused by any system call that's being made like illegal?
Exactly. So, geez, I don't have the full detail here, and this probably is a subject for a totally different talk. Yeah. But yeah, the SEComp does generate a whole bunch of logs. It'll all be in the logcat somewhere.
Yeah, it applies. It definitely applies to apps, and I think there are two SEComp lists, one for apps and one for everything else. I think. I mean, the SEComp filters are designed to allow all the system calls that Bionic normally does. So you tend to have to be doing something a bit special to hit this. But yeah, it's definitely there.
True. But if you've got a bunch of assembler code in your NDK in your native libraries, that can definitely trigger this.
Maybe it could be a native library as well,
Mm-hmm.
because it happens after we added some libraries.
Mm-hmm.
Okay. I think that's a really good point. So it at
Yeah,
least
I
gives
mean,
us.
as Chris says, it should still turn up in the logs.
Okay.
It'll be logged, and it will then terminate your app. But there should be enough footprint there for you to work out why it happened.
Okay.
But yeah, just throw that in there. Sorry, I didn't mean to derail the presentation, which, by the way, Alan, is fantastically good. I'm enjoying this a lot.
Oh, yeah. Thank you.
Thanks,
okay,
Chris.
yeah. Anyway, that's interesting. Okay, so what was I saying? Yes, Treble was all about making it easier to for existing devices to update to vendor code. So the problem is that the vendor specific drivers and policy and stuff is actually really expensive to update. No one wants to do it. No one wants to update the kernels. It's not cost effective, but we still want to be able to update the system. So we said, right, well, what we'll do is we'll put all the vendor stuff on one partition, and we'll put all the system stuff on another partition, and we'll just update the system partition, and we'll leave the vendor partition as it was, and everything will be great. I mean, there's more than just system and vendor, but I'm going to stick like that. The only thing is we have to make sure that the new system will work with the older vendor. We never have to work the other way around. You never have a newer vendor than system, but you may definitely have newer system than vendor. This is not going to happen just by good luck. You have to make it happen. So we need to make sure that the system code and the vendor code are only communicating over stable APIs that don't change as the system code goes up. And that means we need HALs, where a HAL is a hardware abstraction layer. This is a stable versioned, clearly specified interface, generally in AIDL or something a bit like it. And a particular version of an interface is set in stone. It can never change. You can get new versions, but the existing version is just what it is. The system, that's the framework code or various processes or even apps sometimes via system APIs, use the HAL interface. They make calls into it. The vendor, as part of their vendor partition, supplies an implementation of the HAL interface. And that implementation may itself talk to the various vendor drivers, but that doesn't really matter as long as the vendor makes sure that when you use the HAL, it does what it's specified to do. An advantage of this from a security perspective is if the HAL is a completely separate process, which is from a security perspective the better way of doing it, the HAL implementation is allowed to talk to the drivers, and the system is allowed to talk to the HAL, but the system can't talk to the drivers, the app can't talk to the drivers, and that means the attack surface for those drivers is much reduced. Sometimes we do generate new versions of a HAL if there's new functionality that we'd like to expose. But what tends to happen is that the system has to check what version of HAL is actually implemented. So if the system would like to use version 2 of the HAL because it has something funky and new in it, it has to check whether this device actually has version 2 of the HAL. If it doesn't, and it can't do that, it has to keep on talking on version 1. Which means that your new device doesn't get to do the thing, but it can't do anyway because it hasn't got the hardware. But you still get the new version of the system. So this is a great idea. Actually, surprisingly enough, mostly works. But it does mean that we have to be absolutely certain that there are no other ways by which core and vendor are talking to each other that are unstable and probably not versioned, and that no one is checking doesn't change. And that includes random files on the file system. It includes sockets of whatever sort between vendor and system processes. It even includes properties. I mean, to be fair, there's a lot of properties that are used for communication, but we're trying to discourage more of them, shall we say. So this is all good, but how does SELinux relate to this? And there's actually two ways. One is, so we don't want vendor code and system code to be communicating other than through HALs. How can we stop that? Well, we just set the permissions up to say that you can't. So the HALs can only be accessed by the processes that the SELinux policy says can access them. The drivers are only made available, the relevant drivers are only made available to the house, so that SELinux stops anything else from talking to those drivers. And most importantly, we said vendor and core shouldn't be establishing sockets and doing weird things between each other. And the way we ensure that is there's policy that says you're not allowed to do that. And here's an example which I picked slightly at random. Never allow established socket comms is a macro, which expands interesting never allow rules. And what it's saying here is essentially you're not allowed to create sockets if you are a domain or process which is not in core domain, which is system, and it's not an app. So basically that's all the vendor stuff. It's not allowed to create sockets to something that is in core, is in the system. And that means if you try and if you create such a socket, it's fine, it won't work. If you try to add a rule to the policy saying allow this to happen, it will fail to compile because the never allow trumps it. So that's so SELinux is used to make Treble work, to make sure that people are playing by the rules and no one sneaks in an interface that will break on update. But of course, the policy itself also has to cope with this split. So when you update the system, you're also updating the system policy because the new version of the system will have new policy. But the vendor policy won't have changed. And when you update, we mustn't break things. People get very upset if they update their operating system and things stop working. So we have to find a way of making this work. And the rules are that vendor policy is allowed to reference system policy. But we've split the system policy up into 3 separate directories. The public directory, that's stuff that vendor policy is allowed to refer to. So anything there, any types defined in the system, in the public policy, vendor is allowed to refer to. And it's our problem to make sure that nothing changes there, that the existing vendor policy will keep on working even if things get changed. That means that changing anything that's public is really, really hard. It needs an awful lot of care. We also have private files. As part of the compilation process, when you compile the vendor policy, we don't include the private policy. So anything that's in there, if vendor policy tries to refer to it, it just won't compile. So we know that nothing in vendor code is referring to these things. And that means we can change them. If there's a type that's only defined in private, then no vendor policy can possibly be referring to it. So it's possible to change it. Doesn't mean you actually make any changes. It turns out that there are ways of breaking things if you're not careful, but it is at least a little bit easier. And then there's a third directory, vendor, which I have to say is not something I understand particularly well, but I believe this is policy that's really only intended for vendor to access, even though it's part of the system policy. One of the facts of life in Android is adding new stuff is easy. It's hard to break existing apps by adding something new. Taking things away is really hard because you never know if there's something somewhere that's relying on this thing that you think is unused or harmless or whatever. So we have to be very careful with policy changes. There's a whole mechanism for ensuring that if for example, if we change the label on a file and vendor policy it refers to the old label, we have to make sure that vendor policy still works, at least on a device which is running old vendor and new system. And so there's a whole layer of, there's a subdirectory called compat, which contains a whole bunch of files that do this. There are public web pages explaining how this works. It is horribly complicated and slightly terrifying. But anyway, I'm not going to go into the details any further than that. So that's I've kind of run out of things to say. I'm sure we'll figure out a way of making this slide deck available at some point, but I stuck a whole bunch of useful links in here, like the SELinux notebook, which is fantastic for figuring out what the classes and permissions actually mean, at least most of the time. And a whole bunch of other links here. And I've also included my contact details. This is me and my personal and corporate email address. Feel free to ask me stuff about SELinux, and I will see what I can do. And that's me.
Okay, well, thank you very much, Alan. That was, for me at least, I found that very educational. So I've been covering some of these things in my various training courses over the many years. And yeah, that's added in a lot of details, which I've always kind of skated over. So thank you very much for that.
Oh, I'm glad.
Okay, anybody have any questions? my God, it's gone quiet.
I have a question.
Go ahead.
So you are doing this SELinux stuff for years now, and sometimes in your talk you said it's complicated on hell by hell, and you said that you do not sometimes understand it fully. So at which point will you understand it? In 4 years, in 5 years?
Well, so I've been trying to figure this out for about 6 years. There are bits of it that I definitely have a vague understanding of, but you know, it's a complicated subject. I have a collection of law I've built up over the years about. I mean, what the policy does is straightforward. It's the why that is much more interesting, and that's stuff that I kind of learned. As why is it this way? Why is it okay to do this thing, but a bad idea to do that thing? And I'm still learning that. I think I understand the mechanics mostly, but just occasionally I get surprises, like Chris's setcomp thing.
Do you know a person that did or does understand it fully?
Or no. But I mean, there are people who understand things better than me. But yeah, it is slightly niche, let's say.
Yeah. Okay.
I mean, you know, this is the same way that no one understands Android. I mean, it's such a big
true.
fact.
Yeah.
You know, and SE policy has, you know, most of it is straightforward and some of it isn't.
Okay.
Also, the other problem is I should say that a lot of the policy is missing comments, or at least missing useful comments. We're trying to fix that. It's a new policy. We try and put in something saying we're putting in this allow rule in because we want this thing to work. Otherwise, you have to do a lot of digging to try and figure that out.
I think I would totally echo that. So from my perspective, a lot of this stuff is kind of folklore, and you can tell that most people just copy and paste stuff, and I suspect most people kind of fiddle around with it until it works and then they ship it. So myself included, by the way. I
mean, that's one reason why the never allow rules exist. It's because you can make a lot of things work by just disabling SELinux or just allowing lots of bad stuff. So yeah.
I really hate those never allow rules. They are the worst. Okay. Right. So I think we've gone way over schedule here, actually, but yes. that was really helpful. So, but I'm just going to stop that recording.